sometimes an event involves two experiments. For example, suppose we're talking about the event of flipping a coin and rolling a die. So we have these two experiments within the one event, you see, of doing those tests. Now think about the sample space. What are the possible outcomes for this? Well, flipping a coin, we know it can be either heads or tails, and rolling a die can be 1 through 6. So we could have heads associated with a 1 on the die, or a head associated with 2, head associated with 3, 4, 5, or 6. The tails, the tail could be associated with each of the items on the die as well. So we have 12 possible outcomes here. And if we want to figure a probability, like what's the probability of flipping the coin and having it turn up heads and then rolling the die and having it turn up 5, then we would look over here, how many favorable outcomes are there? Well, let's see, a head and a 5 right here. There's 1 out of the 12 items that are possible. So the probability then is 1 over 12. And what about the probability of flipping a tail and having the die come up even? Well, tail and even, let's look over here at the sample space. We would have even, even, even here with the tails. So there are 3 items like that in the sample space of 12. So 3 out of 12, or 1/4. Now, there's another way to proceed with this kind of situation. We could be using the word "and" here where the comma is. The probability of flipping a head and rolling a 5 on the die is the way we could read this. And the "and" statement is a rather special situation in probability. And it is associated with a certain kind of event, or certain kinds of events. Now, it's important in evaluating the "and" statement to evaluate whether or not we have independent events. Now, events can be independent or dependent. We're going to talk about both, but let's talk about independent events first. It turns out, you see, that the calculation can be made rather easily for the "and" statement type probabilities if we have independent events. It turns out that all we need to do is multiply the separate probability numbers for the 2 different little experiments. So, but I'm getting ahead of myself. Let's go back to independent events. Independent events are those events where the occurrence of one event does not affect the probability of the outcome of the other. So we have no sort of interference from the outcome of one to the other. And certainly this example of flipping a coin, rolling a die, those are independent events. They're completely separate from one another. It doesn't make any difference whether you roll a head or a tail to affect the probability of rolling any particular thing on the die. That's the idea of independent events. Now when you have independent events, the probability of A and B is calculated as the probability of A times the probability of B. Now let's come back over here and think of these calculations in terms of what we learned over here. You see, the probability of head, comma, 5 could be thought of as probability of head and 5, and we can make the calculation, because these are independent events, we can calculate the probability of head separately and multiply that times the probability of rolling a 5 on the die. The probability of head on the coin is 1/2. The probability of the 5 on the die is 1/6. 1/2 times 1/6 is 1/12. Now, this is kind of handy when the sample spaces become particularly large. You see, here we were able to write the entire sample space, and we were able to look at the sample space and select favorable outcomes and count possible outcomes very, very easily in this particular problem. A lot of times it's not quite as easy as that. And so this idea of multiplying probabilities is a real neat thing. All right, let's do the other one here using this idea of independent events. The probability of a tail and even would be the probability of tail. Well, let me write it like this with the "and" word in here, because that's usually the way we start. The probability of tail and even you see, would be maybe the way we would start. And then we would evaluate whether or not we have independent events. We do here, so we would think, okay, we can calculate this by writing probability of tail times probability of even. Now, the probability of a tail in tossing a coin is 1/2. The probability of an even number in rolling a die, there are 3 even numbers out of 6. That's 3 out of 6 or 1/2. I'll write it as 3 out of 6. This reduces to 1/2. 1/2 times 1/2 is 1/4. And the probability number is the same as we calculated before, of course. Well, let's make some other calculations. Let's continue just a little bit. And I'm thinking now about rolling a die and drawing a card from a deck of cards. Now think about sample space here. If we were going to write the entire sample space for experiments involving rolling a die and drawing a card, rolling a die, there are 6 possible outcomes here, and each of those outcomes has to be associated with each of the 52 cards. So we would have a 1 on the die associated with a 2, a card 2, and the 1 would be associated with 3, and the 1, and I'm not even talking suits here yet, am I? So the 1 is associated with the 2 of hearts, the 2 of diamonds, the 2 of spades, the 2 of clubs. The 1 is associated with, do I really want to go through all of these? Go like this. No, I don't. What I want to be able to do is make the calculation without looking at the entire sample space. So think about whether or not we have independent events, rolling the die, drawing a card, and certainly the outcome here, the occurrence of whatever happens over here, has nothing to do with the probability of some occurrence over there. So we have independent events, and when we have this AND statement, we can write this as the probability of rolling a 4 times the probability of drawing a king. And now the probability of rolling a 4 is 1 out of 6. The probability of drawing a king is, there are 4 kings out of the deck of 52, so it's 4 out of 52. This is 1 over 13, and when we multiply, we get 1 over 78 as the probability. Probability of even and diamond, let's see, that would be the probability then of even times the probability of a diamond. And the probability of even, when we're rolling a die, there are 3 even numbers on the die, so it would be 3 out of 6. And the probability of a diamond, how many diamonds are there? There are 13 of them in a deck of 52, so it's 13 out of 52. Both of these will reduce a bit, and when the smoke clears on the reduction and multiplication, it turns out to be 1/8. Now, consider this one. Suppose we're drawing a card, and then we're drawing another card, and we're talking about the probability of drawing an ace and a king. Now, we might think, okay, we're just going to draw 2 cards from the deck of cards. Are we going to put the first card back when we draw it or not? Let's assume that we're going to put the first card back. Okay, if we do that, then it's worked this way. The probability of ace times the probability of king, or 4 over 52 times 4 over 52, or 1 over 162. Now, this probability stayed as we would expect it for drawing a king out of a full deck of cards, simply because we replaced the ace. What if we didn't replace the ace? What if it's without replacement? You see, if we're talking about without replacing that first card drawn, without replacing that ace that we drew the first time, then we change the probability of this. And so this idea of drawing 2 cards from a deck without replacement is an example of a dependent event, because the selection, that first selection of a card, affects the probability of the second selection of a card. Now, to calculate this, to make this calculation of probability, we do this. We think about the probability of drawing an ace. That's 4 in 52. Now we think about the probability of drawing a king, given that the ace has already been drawn. You see, so the ace has already been drawn. That's 1 card out of the deck. Now the probability of drawing a king, there are 4 kings still in the deck, and there are 51 cards now in the deck. So 4 out of 51. This is a notation that we're going to use when dependent events are involved. It is the given idea, given that the first item has already occurred. So, to summarize with dependent events, the probability of A and B is the probability of A times the probability of B given that A has already happened. Or it's the probability of B times the probability of A given that B has happened. You see, either way you calculate it, it's going to be the same thing. So when we calculate something like the probability of ace and ace, you see, without replacement here, we're talking about the probability of ace times the probability of the second ace given that the first ace has been drawn. So multiplying the probability numbers, this would be 4 out of 52, and if the first item drawn was an ace, then there are 3 aces left, 51 cards, so 3 out of 51 is the probability of drawing that second ace. Multiplying here, the probability is 1 over 221. Sometimes probability problems have the word or involved. We talked about the and word and what that could lead to. The or word can lead to interesting situations as well. Suppose we want the probability that in a deck of cards we draw an ace or a king. Well, let's see, ace or king. The favorable outcomes would be aces or kings out of the whole deck. Now, if we're looking at the sample space like this, you know, we have our 4 suits of cards. Each suit has 13 cards in the suit. If we're thinking about aces or kings, we can draw any of those cards, or we can draw any of those cards and have a favorable outcome. So there are 8 cards that give a favorable outcome out of the whole deck. Okay, sounds reasonable. This then is 8 out of 52, which can reduce. And it reduces to 2 in 13. All right. Now, another way to look at the situation, you might think, well, gee, maybe there's a shortcut. There was a shortcut when we were talking about the and statement. We multiplied probabilities in certain circumstances when the and statement was involved. And it turns out here that we can think of this as the probability of ace plus the probability of king, because we have a particular set of circumstances that lends itself well to this. And the aces, let's see, this turns out to be, there are 4 aces out of 52. There are 4 kings out of the 52 cards. That's the 8 out of 52. And let's see, dividing 4, both numerator and denominator, it's 2 over 13. Okay, so the same idea. So we can add probabilities. Now consider this. The probability of a queen or a heart. Queen or heart. Well, if we look at the sample space, we're thinking about the queens. Those would be favorable outcomes. Hearts, those would be favorable outcomes. Now, if we count all of these cards along with all of those cards, then we would count 4 and 13. But when we count these 4, we're talking about the Queen of Hearts. When we talk about these 13, we're also talking about the Queen of Hearts. So we have an item that we're counting twice. So if we're going to get just the items that are in the sample space that we want, just those favorable outcomes, and not do some double counting, we would think of all of these hearts, the 13 hearts, including the Queen of Hearts, and the other queens. So it'd be 13, 14, 15, 16. So we're talking about 16 favorable outcomes out of the 52 cards. And I'll leave it in unreduced form just for the time being. Now, so does this imply then that we could make the calculation as the probability of a queen plus the probability of a heart? Certainly not, because the queens would be, this would be 4 over 52, and this would be 13 over 52, which would give a miscount, a double count on the Queen of Hearts. It turns out to be 17 over 52 and not 16. So this brings us to a situation where if the two situations have something in common, then we're going to do some double counting, and we have to accommodate that. Now, this leads us to another idea of certain kinds of events. We're talking about mutually exclusive events, or events which are not mutually exclusive. It turns out that the first example over there involved mutually exclusive events. Second example involved events that were not mutually exclusive. Events that have no outcomes in common are mutually exclusive events. And the Venn diagrams are very good in showing or illustrating what a mutually exclusive events are and what non-mutually exclusive events are. In our ace-king idea over here, we were talking about the probability of drawing an ace or a king. If we're thinking about the box contains all the cards in a deck, and this circle contains the aces and that circle contains the kings, notice that they have nothing in common. On the other hand, in the other example, when we talked about the queens and the hearts, this circle contains the queens, this circle contains the hearts, and the queen of hearts is in both of those two sets. So in this situation, the intersection of the two sets would be the empty set. In this section, the intersection of the two sets would contain something, would have something in them. All right, so that's the idea of mutually exclusive. Now, let's get to the formula idea, or some notion of a formula involving mutually exclusive events and non-mutually exclusive events. With mutually exclusive events, we found earlier that the probability of A or B can be calculated as the probability of A plus the probability of B. Just add the separate probabilities of the two items that are in parentheses. All right, so adding probabilities for mutually exclusive events. Now, for all other events, and in fact, for all events, we could use this idea. The probability of A or B is the probability of A plus the probability of B minus the probability that both things happen at the same time. You see, or can occur at the same time. So we have to subtract out that probability. And you know, if we apply this idea to our calculation earlier, let's come back over to this side and apply the idea to this queen or hearts business. You see, it's the probability of queen plus the probability of hearts minus the probability of the queen of hearts. Now, the probability of the queen of hearts, there is only one queen of hearts, so we would be subtracting out this 1 over 52. And now this gives us the 16 over 52 that we were looking for. So it's the one probability plus the other probability minus the duplication is what we're subtracting out here in this part of the problem. Understand that this second formula can be used for mutually exclusive events, because in mutually exclusive events, the probability that both items will occur is 0. So we're not subtracting out anything. So this is kind of a universally applicable formula when we're talking about the OR statement. Let's look at a couple more examples. The probability of red or face card. Now, we could perform a little analysis right here and think about, do we have mutually exclusive events or not? And to be able to tell, is there such thing as a red face card? That is, can both of these happen at the same time? We have red, we also have face. Yes, there are red face cards. So these are not mutually exclusive events. So what we're going to have to do is use the general formula, the idea of the probability of red plus the probability of a face card, and subtract out the probability of red face cards. So let's see, the probability of red. Well, half the deck is red, so that would be 26 out of 52. And we add the probability of face cards. There are, let's see, there are kings, queens, and jacks, and each of them has 4 involved in them. 4 times 3, that's 12. So that's 12 out of a total of 52. And we're going to subtract the red face cards, and let's see, 2 of each of those groups of 4 turns out to be red. You see, we have the hearts and diamonds of the kings, the queens, and the jacks. That's 2, 4, 6. So we're subtracting out 6 out of 52 in this area. And now it's 26 plus 12, that's 38, minus 6, that's 32. So it turns out to be 32 out of 52. And it reduces, but the reduction is not terribly important to us. It's this part that we're interested in. Now, what about the probability of heart or club? Heart or club. Now, we could start the idea by saying, gee, do we have mutually exclusive events? Can we have a card that's both a heart and a club? No, we can't. So we don't have or we could just say, well, let's just use the general formula, because the general formula works in all cases. And we could then approach it like this. We're just going to add probabilities and subtract out duplication. So it's the probability of hearts plus the probability of clubs minus the probability of both. And the probability of hearts, there are 13 hearts in the deck, so it'd be 13 out of 52. That's 1/4. Plus another 13 out of 52 for the clubs. And then subtract out, the probability of both can't happen. So the probability there is 0. 0 out of 52, or simply 0. 13 out of 52, 13 out of 52, that's 26 out of 52, which is 1/2, and that's half the deck, as we know, because we're taking half of the red cards and half of the black cards to get a total of half of the deck. At Hopewell Electronics, all 140 employees were asked about their political affiliation. The employees were grouped by type of work as executives or production workers. Here's a chart of the results of the survey. Now, over on this side of the chart, employee type, executive, and we're going to mark that with E, and production worker, mark that with PW. And over here, their political affiliations, Democrat, Republican, Independent, and the number of people involved. Now remember, this is executive and this is production workers, and Democrats, Republicans, Independents. At the bottom, we have totals for the Democrats, the Republicans, and the Independents. And over here, there's another total having to do with the executives and the production workers. And the total number of employees altogether is 140. So that's the layout of the chart. Now, we'd like to answer a few questions involving the information in the chart. First question, probability of D. D, Democrat. Okay, when we say probability of D and make the calculation, we're assuming that an employee in this company is chosen at random. And what is the probability that that person will be Democratic? So we come over here and we say, okay, well, we've got the Democratic idea. These folks in this column are Democrats. So we have 5 executives and 63 production workers that are Democrats for a total of 68. So if we're talking about the entire group of employees at the whole plant, then the probability that that employee is Democratic is favorable outcomes over possible outcomes. So it's 68 over 140. So 68 over 140. And that will reduce, or it will change into a decimal. If we want to write it as a decimal, it's 0.486. All right, the probability of executive. Well, the executive, let's see, we come back over here. The executives are along this row. So we have 5 Democrats, 34 Republicans, 9 Independents, for a total number of executives of 48. Now, these two problems are just designed to get us familiar with the layout of the chart. So we have a total of 48 executives. So 48 favorable outcomes out of a total possible outcomes of 140. So the probability of selecting an executive out of all of the employees is 48 out of 140, because there are 48 executives out of the 140 employees. And again, this can be written as a decimal as 0.343. Now, what about the probability of Democrat given executive? Democrat given executive. Let's come back over here. Given executive, the probability of Democrat given executive. When we're given something, that's a condition on this probability. It is the condition that the person being selected is definitely an executive. All right, so we're talking about these rascals, and the probability of Democrat is 5. There are 5 Democrats in this group of executives, you see. So Democrat given executive is 5 over 48. So 5 over 48. And again, a decimal is associated with this one, and it turns out to be this. Now, are events D and E, Democrat and executive, independent? You know, when we talked about independent events earlier, we were talking about such things as drawing cards and rolling die and that kind of thing. And we were saying that does the outcome of one have anything to do with the probability of the outcome of the other? And that was sort of the acid test. Well, we can't quite put our finger on how that applies here, can we? And when we were talking about drawing a couple of cards from a deck, it depended upon whether or not the first card was replaced or not before the second card was drawn. And again, we don't have that luxury. It turns out that to test for the independence of events in a situation like this, what you do is you ask yourself, is the probability of D equal to, is it equal to the notion of the probability of D given E? Now, let's see, the probability of Democrat, we had calculated that up here as 486, and the probability of D given E was calculated here as this, and certainly these are not equal, and therefore no, these are not independent events. All right? They're not independent events, then how are we going to calculate the probability of D and E? Well, the AND business, remember when we're talking about independent events and we're talking about the AND statement, we multiply probabilities. It would be the probability of D times the probability of E. But these are not independent events. These are dependent events. So we have to use one of the two formulas that we talked about before. Or we can use the sample space, or our chart, you see. Now, intuitively, let's analyze the situation. The probability that someone chosen is a Democrat and an executive. All right, Democrat and executive. Let's come back over here. Here's the column of Democrats. Here are the executives. How many folks are both Democrats and executives? Well, just this. You see, because it's the intersection of the executives with the Democrats. Democrat and executive. There's only 5 of them. So a random sample that's just choosing one out of the group, there are 5 favorable outcomes and 140 possible outcomes. So it'd be 5 over 140. So let's see. Let me put that out over here. This is what we're finding intuitively. Now, what about some kind of formula? Well, we said that because these are dependent events, that there are actually 2 ways to do this now. It's the probability of D times the probability of E given D, or it's the probability of E times the probability of D given E. Now, what does all of this mean? Well, let's see. I'm going to just do the last one because I have a little bit of room here. The probability of E, the probability of executive. Now, we figured that earlier as there were 48 executives total in the company, so it's 48 over 140. All right, now, what about this part? This is the tricky part. The probability of Democrat given executive, Now, we actually calculated that earlier as well, but let me just rehash that a little bit with you. Come on back over here. Let's go to the chart. And we want Democrat given executive. So given, so we have a constraint or a condition on the probability here. Given executive, we know we've got an executive. Now, what's the probability that that executive is a Democrat? Well, the Democrats that are executives, there are 5 of them, you see, and it's the condition that we're only talking about executives, so it's 5 out of 48. And that's what's important to realize here, is that it's 5 out of 48, not 5 out of 140. So 5 out of 48. And the 48s cancel here, so we have 5 out of 140, which is the same fraction that we have up here. Both can be reduced, but that's not the point here, really. Okay, what about the probability of D or E, Democrat or executive? Well, again, we can take kind of an intuitive view of the situation, and alternatively, we can use a formula. Now, Democrat or executive, let's come back over here and look at or count Democrats or executives, which would meet the favorable outcome idea on this probability. So let's see, Democrat or executive. So it's these 48 or these 68, but we don't want to count the 5 twice. You see, so it would be the 63, the 34, the 9, and the 5 only counted one time. That's one way to think about it. So 63, 5, 34, 9. That's a way to calculate it. The other way is to use the formula, and I didn't bother to add the. Let me add them. Let's see. This would be 68, 34. That's 90. That's 102, and 9. That's 111. So it should be 111. Intuitively, we're finding that it's 111 out of the 140. So let me just write that down. Now let's use the formula. The idea with an OR statement is we can use the general formula, you see, for whether or not, we don't have to evaluate whether we're mutually exclusive or not. We're not mutually exclusive because there are folks that are Democrats and executives, and therefore the two groups have something in common, and we can apply the general formula, and that's what we're going to do. Okay, so it's the probability of Democrat plus the probability of executive minus the probability of both. Now I'm just going to write the word both here. You might get into the habit of doing this. You might want to write, it's a little more formal, a little more correct, to write the probability of D and E, you see, and D and E we calculated up above. But at any rate, this is a rather intuitive kind of way to look at it, though, I think. The probability of D we figured before as 68 over 140. There were 68 Democrats out of the 140 folks in the building. The probability of executive, there are 48 executives, so that probability is 48 out of 140. And then we subtract out the probability of Democratic executives. How many Democratic executives were there? Well, we found that to be 5. We saw it over there in the chart. 5 over 48. Excuse me, 5 over 140. And then when the smoke clears here, we find this to be 111 out of 140, and that's what we found when we looked at the situation kind of intuitively. You draw 2 cards from a standard deck of 52 cards without replacing the first one before drawing the second. First question is, are the outcomes on the 2 cards independent? Are they independent? Well, we need to meet the definition of independence if the outcomes are to be independent. The notion of independent events is that the outcome of one event is not dependent upon the outcome of the other. That is, the happening of one event does not affect the probability of the happening of the other. And certainly if we're not replacing that first card, then we're changing the sample space for the drawing of the second card, and therefore the 2 events are dependent. So we would answer like this. No, because drawing the first card changes the probability of drawing the second card. Let's find the probability of drawing 3 on the first card and 10 on the second card. Now the AND tells us that we're going to multiply probabilities, and since the probabilities are dependent, we have the second item is a sort of a given item. It's the probability of 3 times the probability of 10 given a 3 on the first card. The probability of drawing a 3, well, there are 4 3s in a deck of 52 cards, so the probability is 4 out of 52. Now once that 3 is drawn, it leaves, and not replaced, it leaves only 51 cards in the deck. And so the probability of drawing a 10, there are 4 10s, but the number of cards in the deck is now 51. Now 4 over 52 is reduced to 1 over 13, which gives 4 over 663, or 0.006 for the probability number. Now this problem looks almost the same. Find the probability of 10 on the first card and 3 on the second. It's sort of the same problem in reverse. It's going to be the probability of 10 times the probability of 3 given 10 on the first card. And it's the same exact idea. The probability of drawing a 10 from a deck of 52 is 4 out of 52 because there are 4 10s in the deck. The probability of drawing a 3 given that a 10 appeared on the first card is, well, let's see, there are 4 3s in the deck, but now the deck only holds 51 cards, so it's 4 out of 51. And once again, we reduce and then multiply straight across and get the same probability number that we had before. At Litchfield College of Nursing, 85% of incoming freshman nursing students are female and 15% are male. Recent records indicate that 70% of the entering female students will graduate with a BSN degree, while 90% of the male students will obtain a BSN degree. If an incoming freshman nursing student is selected at random, find. Now we're going to ask some questions in a moment, but let's organize the information we have before us. We notice that 85% of the freshman nursing students are female, 15% are male. 70% of the female students will graduate, 90% of the male students will get a degree. So we can organize the information like this. 85% of students are female, and of those, 70% will graduate. 15% are male. Of those, 90% will graduate. Let's answer some questions. First part says, what's the probability that a student will graduate given that the student is female? Probability of graduating given that the student is female. Now, the probability number is actually given in the outline of the problem above, because it says that of those female students, 70% will graduate. So a student chosen at random will have a 70% or 0.7 chance of graduation. What's the probability that a student is female? Now, a student is chosen at random from all of the students. A student chosen at random is, well, we want the probability that the student is female and that the student will graduate. So the probability that the student is female times the probability that the student will graduate given that they're female is the way to make the calculation. Now notice the dependence idea here, because the graduating students in the outline above depend upon, the percent that are graduating depend upon their gender. So we have a dependent situation here. Now the probability of being female is 85%. 85% of all students are female. Now once you're in that female category, the probability of graduating is 70%, so 0.7. And then the product is 0.595. Now here's another way to look at the situation. Suppose we make an outline. I want to show you actually two ways of calculating these probabilities involving these students. One way is to deal with the outline at the top of the screen. Another way is to take a rather fundamental view of the situation and think about favorable outcomes over possible outcomes in terms of numbers of students. Now, to put numbers onto these problems, I'm assuming that Litchfield College has 100 students, because 100 is just an easy number to work with and corresponds well with the percent numbers. We could just as easily use 148 or 10,000 or any number that we'd like. It's just that 100 works out pretty well and is easy to, as I say, calculate. All right, let's fill in the information, or some of the information in this chart. The number of female and male students. Well, if the total number of students at the college is 100 students and 85% of them are female, it means that 85% of 100, 85 hundredths times 100, or 85 students are female. And in a similar way for the male students, 15% of 100, or 15 students are male. Now, what about for the graduates of those two categories in each gender? Well, we're told from above that of the female students, 70% will graduate. So that turns out to be 70% of 85. So the number of graduating female students will be 59.5. In a similar way for the males, 90% of 15 will graduate, or 13.5 students is what we're talking about. Now we can make our calculations in an alternative way for the items in question. For example, from that B part, it was the probability that the student is female and the student will graduate. Well, let's see, female and will graduate. This is the female column, and the graduates are along this row. So the females that will graduate, we have 59.5 of those. And calculating the probability number as a favorable outcome over possible outcome kind of calculation, it's 59.5 students will graduate that are female, and out of the total of 100 students at the college. So the favorable outcomes over possible outcomes gives us the same result as we had before by multiplying percents. Here's our original outline, and let's consider another problem. The probability that a student will graduate given that the student is male. Very similar to an earlier problem involving the females, but we want to just work through this in a way that we did before, in a similar way that we did before. Now, actually, the probability number is given in the outline because we're told here that of those male students, 90% will graduate. So the probability that a student will graduate given that that student is male is 90%. So we're putting that student automatically putting that student into that category, you see, just in the outline above. So the probability is 90% or 90 hundredths. Now, let's look at it another way, just using the fundamental idea of numbers of students. Student will graduate given student is male. Well, here's the male students that will graduate. You see, given the student is male. We're limiting our sample space here by saying given that the student is male. And that's a very important aspect of calculating probabilities, especially when we're talking about favorable outcomes over possible outcomes. So the favorable outcomes would be 13.5 students. The possible outcomes, the possible number here, we're given that the student is male, so there are 15 male students. So our probability number is 0.90, as we found earlier looking at the outline. What about the probability that a student is male and the student will graduate? Well, again, we think of, both of these things happening, the male idea, the gender idea, and that the student will graduate. Well, that puts us into this 13.5 students. And, but the sample space here is the entire population of the college. So favorable outcomes, 13.5, possible outcomes, 100 students in the college. And the probability number is 0.135. Let's work the problem another way using the outline. Probability a student is male and the student will graduate. Remember, and implies that we're multiplying probabilities, and we're talking about a dependent situation here. So it's the probability of male times the probability that the student will graduate given that the student is male. Probability of a male student is 15% or 15 hundredths. The probability of graduating given that the student is male is 0.90, 90%, you see. And the product is, as expected, 0.135. What about the probability that a student will graduate, period, regardless of gender? It's important to understand that this is regardless of gender. And it turns out that we're going to look at the problem like this. We want to notice that those who will graduate are either males who will graduate or females who will graduate. And we can write it like this. The probability of being a male graduate or a female graduate is what we're talking about here. And when we talk about or, we're talking about adding probabilities. And because these two incidentally can't have anything in common, there can't be a graduate who is both male and female, so we don't need to subtract duplication out of this situation. But the probability of being a male graduate from our calculations before is 0.135. The probability of being a female graduate is 0.595, and the sum of those 0.73. Now, what about looking at it a different way? Now remember, the probability was 0.73, and let's see if we don't get the same thing looking at the numbers. Okay, probability that a student will graduate. Well, where are those graduates? They're right here. So 59.5 male students graduate, 13.5 females, excuse me, 59.5 female students will graduate, 13.5 male students will graduate. The sum is 73, so 73 students overall will graduate. That means that the probability of graduating is 73 over the total number of students at the college, 73 over 100.73 as we expected. The events described by the phrases is female and will graduate and will graduate given female seem to be describing the same students. Now certainly that part is correct. We are describing the same students. Female students that graduate. So why are the probabilities, P, probability that the student is female and will graduate, and the probability that the student will graduate given female, why are they different? Why are those two different? Well, it has to do with sample space, and we can see it easily by looking at the outline of the numbers of students in these categories. You see, in both situations, the probability that is female and will graduate, probability of will graduate given female, they have the same favorable outcomes. The same numerator of the fractions is going to be 59.5. Those are female students in the graduation category. All right, now, but when we are talking about the given female business, our sample space is only 85 people because there are 85 females on campus. So the fraction is 59.5 over 85. On the other hand, when we talk about and will graduate, just generally on the campus, we're talking about a sample space of 100 students. So the sample space is different in the two calculations, and that's the whole idea. So we can write our answer like this. In the case of and, the sample space is all students, both male and female. In the case of given, the sample space is restricted to females only.